So I'm gonna switch gears a little bit during my talk, and what I'm going to do is to show you how we can use deep learning methods and more generally AI into a control loop, okay? And specifically for the design of automated insulin delivery therapies for type 1 diabetes. So first of all, let me give you a little bit of context and motivation. So diabetes is a chronic metabolic disorder, which is characterized by the inability of the body to produce enough insulin, or the insulin that is produced cannot be used effectively, okay? As a consequence, the blood glucose concentration in the blood remains high, and this has long-term effects and complications, leading to damages to organs like the cardiovascular system, the kidneys, foot, and so on and so forth. Okay, so currently we have about more than 400 million individuals in the world living with type 1 with the diabetes, and this figure is both type 1 and type 2 diabetes, and it is projected to increase twofold by 2045. Okay, so we are here in the North American continent, where almost 50 million are living with diabetes, and 1 in 5 is at risk of developing type 2. Okay, type 2 is characterized by some production of insulin, but the insulin is not sufficient. Overall, we account for almost 50% of the global healthcare expenditures for diabetes. And it's safe to say that it's a compelling problem, and a lot of people have been working on it from different perspectives, okay? So from sensors measuring glucose concentration in the blood, to actuators, insulin pumps, syringes, the development of new drugs, and also, as far as we are concerned in the control community, automated insulin delivery systems, which I'm going to tell you in a second. But how does the regulation of glucose happen in a healthy body? So the human body uses a combination of manipulating variables, opposing dual control, to achieve the glucose regulation. So it's similar to the gas and brake pedal in a car. So when glucose is high in the blood circulation, for instance, after a meal intake, this triggers insulin secretion by the pancreatic beta cells. In turn, insulin takes the excess glucose and stores it in the liver, in the fat cells, and in the muscles for uptake at a later stage. Okay, so that glucose concentration goes down and it remains into a healthy bound. This is similar to the brake pedal in the car. Now, between meals or during physical exercise, for instance, sleep and rest, when we have a low glucose concentration, glucagon is secreted by the pancreas, which is here. So glucagon is the counter-regulatory hormone to insulin. So it goes back into the liver where the previously stored glycogen molecules are. It breaks them down and releases glucose in the portal circulation, like the gas pedal in the car. So that glucose concentration is high again and the body can function. So how does it look like for a healthy individual? So here I plot in the y-axis milligram per deciliter, which is the unit of measurement for blood glucose. And in the x-axis, we have time of 1 day of a representative healthy person. We can say average glucose around 85 milligrams per deciliter. According to the American Diabetes Association, we can tolerate fasting up to 100 milligrams per deciliter, and after meals between 140 milligrams per deciliter. You can see, although there was physical exercise, food, and daily life, glucose was in a narrow range. Okay, so. How does a subject with diabetes try to achieve the same narrow range? So I'm talking about the case of type 1, where subjects monitor their glucose with a finger stick, so subcutaneous glucose monitors, or a continuous glucose monitor, a CGM, which provided the trace that I showed you in the previous slide. So based on the measurement that they received from these sensors, they have to come up with an optimal dose that they have to inject via syringe or through a subcutaneous pump, which you can see here in the picture, according to the so-called basal bolus therapy. So we have a background insulin concentration, the basal, to provide enough insulin to sustain between meals, and then a bolus when an increase of carbohydrate or stress or corrections happens. So optimal insulin dosing is challenging because it requires a constant decision making by the patient and the caregivers in response to several disturbances such as meal, exercise, stress, and sleep. So if the therapy fails to provide enough insulin and glucose is above 180 milligrams per deciliter in hyperglycemia, the long-term complication, I've listed some, are cardiovascular disease, kidney disease, blindness, and so on. But if we inject too much insulin, we may die, okay? Because the action, we cannot take away the insulin that we have previously injected. So how are we going to go about it in an automated fashion? So we want to help the patient in their decision making with all the sensors that they are using for the measurement and the assessment of their biological state. We want to give them control actions automatically. So let us suppose that here on the left, I have the narrow range that I showed you before. This is my target. And here I have a patient which is sitting there in the loop, affected by all the glycemic disturbances, okay? The patient is measuring with the sensors, the glucose measurement, but also now with the widespread use of wearable devices, we can have heart rate, galvanic skin response, oxygen saturation, and so on and so forth. So taking those measurements and knowing where we want to go, we can design controls action and deliver them with a smartphone application that command the actuation, either a syringe or an insulin pump, okay? So closed loop glucose control is challenging, and because of multiple reasons. So first of all, the human body has an intrinsic variability. The disturbances are very complex. Meals have a wide range of compositions. Physical activity, fitness, the context, and the competition have an effect which is variable between patients, between people, and stress as well, which is very difficult to predict. Typically, it releases cortisol, and cortisol is counter-regulatory to insulin, so glucose concentration increases, okay? Measurements are limited. At best, we can get one sample every 5 minutes. And the actuation, as I said earlier, is just one-sided. So we give insulin, but we cannot extract it. So one strategy that is particularly suitable to tackle this problem is model predictive control. Okay. So as I'll just give you an introduction. As all the control strategy, the objective, the idea is to compute control inputs that we're going to give to the process, in our case, the patient, so that the output of interest, glucose concentration in our case, reaches as close as possible to the set point, okay? We do this using, in a feedback loop, using measurements that we collect from the patient, so that we can update our control law. Now, a feature of the model predictive controller is that it uses a model of the dynamics, okay? So the model is used to provide a prediction of what the future output will look like if certain control actions were taken, okay? And by means of an optimization algorithm, the so-called best control action according to a certain performance index is chosen. So we use a dynamical model of the process to predict its future evolution, and then we choose the best control action. So let me put just a few formulas here, and then not much more in the next slides. So assume that we are here at time t. We have the reference in the dashed line that we want to achieve in a certain time horizon between t and say t plus capital N, okay, and n steps ahead in the future. We have our model that predicted the future evolution. We want to minimize the error between the reference and what we are measuring now, penalizing also the control input. So we have a prediction model giving this future look ahead. We have some constraints on the actuation and in the maximum allowed value of the control output. And solving the numerical optimization problem, we come up with a sequence of manipulated inputs, control actions in the future. We only take the first one and we repeat the same process as time t+1. Okay, this is called receding horizon optimization and has been used widely, especially in the chemical industry, but now even autonomous driving cars are using that. So the important part here is that the control strategy requires a prediction model. So this is our first ingredient. It requires a way to solve online optimization efficiently. And it requires us to calibrate various parameters such as weight, the length of the horizon, and so on and so forth. So what I'm going to do in the remainder of the presentation is to look into the prediction model using deep learning. Okay? So the idea is to get a good prediction model from data, okay, in a data-driven fashion. But instead of fitting a model, we're going to fit the entire output prediction, okay, via deep learning. So we are interested in finding a map, H, that is mapping the state and the future control input to a predicted output, Y hat, okay? So now I can rewrite the same thing in a more compact notation by stacking all my predicted output at subsequent prediction horizons, okay? And I fit affine predictors in the following form. So I have one component, which is a nonlinear function of the current state, or equivalently, the past input-output pairs, that in my case are the glucose monitors, the carbohydrate, and the insulin. And one other component, which is affine in the control input, which I fit in a second that I'm going to tell you. So in this way, by having a nonlinear function of the current state, but a component which is affine in the control input, my MPC problem can be solved efficiently. It becomes a QP, a quadratic programming. And in spite of the nonlinearity, we have a nice closed form solution. So what we have done, we have estimated this F function with LSTM network, okay? So we have access to a computer simulator that was FDA approved, actually accepted as a substitute for animal trials. So we have 10 patients. We can run simulation as we were in the clinic. We run open loop, meaning we give meals to the subject in a pattern, again, recreated with another simulator, mimicking daily life. And we collect glucose measurements. Subsequently, using a sampling rate of 15 minutes, we create 8 different predictors, each 15 minutes ahead. So from 15 to 2 hours ahead in the future. So once we have created this LSTM, we fit here the G function affine in the input by creating another set of data in closed loop. So in this case, we also give insulin, and we are interested in estimating the effect of the drug onto glucose dynamics. Once we have fit our controller, we are ready to formulate our quadratic programming problem. So Y hat of t is the predictor that I showed you before, which is comprised of a stack of LSTM plus a linear component. Okay. Since we want to have glucose between 70 and 180 milligrams per deciliter as a safe range, we use a reference that is 110 during the day and a little bit more conservative during the night, okay? A piecewise function, 125 during the night. We tolerate glucose to be between 0 and 500 milligrams per deciliter, and we can inject at the most an insulin dose of 25 units. Prediction horizon up to 2 hours ahead in the future. Q and R are tuning parameters that we can have. We can decide how to tune. So let me show you some preliminary results. Using again the simulator, we have 10 patients. We generate random scenarios for the meals. On the top, we have glucose in milligrams per deciliter, and on y-axis, and in x-axis, we have the time in hour. The thick magenta is the mean, the average over the population, and the pink is the standard deviation, plus minus, across the patient. So the controller did not have any information about the meals, okay, and was reacting, therefore, only based on the feedback from the glucose measurement. On the bottom, you can see the insulin infused by the pump in simulation to achieve that tight control. So we are interested in this range, 70 to 180 milligrams per deciliter, and we can see how we can achieve it, 73% plus minus 11 of the time, which is a very good result. Most importantly, we never go below 54 milligrams per deciliter, and below 70 milligrams per deciliter, very, very rarely, 0.14 plus 0.37% of the time. So far, so good. So this was automated insulin delivery in simulation. How does this compare to the so-called optimal clinical practice? So what would have done the patient knowing the exact amount of food and an exact formula to calculate the insulin? Well, this is what will be in blue. You can see that our controller is comparable to the results that we can achieve with the optimal insulin injection. And we are even doing better because we are much tighter in the range compared to the variability that we have in the blue. So here you can see the doses that are given with an anticipatory way compared to our controller. The reason being the comparison is done with the subject knowing, let us assume they know exactly how much to give and at the right time. Our controller instead has to wait a little bit until the effect of the meal appears in blood glucose and then react to it. But regardless, the comparison is very satisfactory. So where do we go from here? Well, we have presented a way that allows us to learn an entire output prediction over an MPC horizon as a nonlinear function of the current state, but affine with respect to the sequence of future control moves to be optimized. The learning occurred based on input-output data collected on the process to be optimized. So in this way, a nonlinear model predictive control problem can be very well approximated by the linear time varying MPC, where at each sampling step, a QP problem based on the linear prediction is solved and run at runtime. So the computational burden is only in the fitting of the LSTM, which is done offline, okay? Online, we are just solving a QP problem in a very efficient way. We have applied this method in silico for glucose control in a virtual population of 10 subjects. So the next step will include improving the controller tuning, testing it in various scenarios, including physical activity, stress, and go for in vivo testing. So this concludes my presentation, and I'm happy to take questions.
You mentioned it being efficient. I know probably training it in real time. Could you retrain in real time if you needed to?
So it's a good question. Training is very time-consuming, obviously. I think what we can do, running the optimization in real time is efficient, and we can do it. We can retrain while the controller is using the same model, and we allow maybe 1 day for training.
Okay.
And we re-update the dynamics. And in the next iteration, maybe for the next week, or maybe for the next 2 weeks, we can use this new set of LSTM and linear models.
Very interesting method.
Yeah.
I think it has lots of applications.
Yeah, thank you.
Any other questions?
Yeah.
Yeah, I think you talked a little bit about the feedback loop to the predictive system.
and the prediction is for the next n steps, if I remember correctly. So is there an assumption that when the system is being used, there is a state where even with the feedback, the learned model is going to be stationary in some way?
Yeah, well, in that sense, yes, you assume that once you have trained the model, that is your dynamics. The reason why we are using LSTM is that they are able to learn a much more complex dynamic as opposed to linear models. So if I show you, I have one extra slide here, for instance. This was just a simulation that we ran very quickly, where the yellow is a linear ARX model that we have trained on the same amount of data that we collected to train the LSTM, but with the limitation of a low complexity model, lower order, and worse performances. So in that sense, yes, you assume your dynamics is fixed. LSTM are quite complex in the control world to get it to run. But as we were mentioning earlier, we can find a way to update it at runtime. Yeah.
I see. Thank you.
Can I ask you a question?
Yeah.
So from the clinician standpoint, we know that low glucose is much worse than high glucose. So would your model can be programmed that be more sensitive when the glucose goes really down?
Yes, so what we do is that in this formulation here, we have 2 points where we can account for that. Well, actually 3 parts. Number one is the reference set point. So I deliberately decided to have a higher 125 at night because I don't want to, especially at night, I don't want to over-deliver. So we can adjust the set point that we want to reach. This is number one thing. Second thing here, there is, I have a weight, so I'm penalizing the deviation from my reference in different way, and I can use asymmetric cost functions that are giving more weight to higher glucose levels and lower weight to the low glucose level. So I'm sure I'm away from the dangerous zone in between. The third part is that we can have a layered architecture by which we can shut off the pump, for instance, when we detect that the derivative, the glucose concentration is trending down, we can shut it off, and whatever is insulin on board will get cleared eventually. So yes, we have a variety of safety layers that we can implement other than the model. The model has to capture the true dynamics of the system to be efficient.
One quick question. If the model makes a mistake, let's say we...
Yeah, you're there.
Yeah, sorry, yeah. If the model makes a mistake or is there some sort of error in the control process, can you talk about the explainability of this model, right? So how can you trace back potential errors and things like that?
Yes.
Because you have an LSTM in the loop now, so it's a kind of a black box.
Yes, that's something that we're thinking about. So we are confident that having the feedback, we can compensate for the errors of the model. That's the whole thing when you have a feedback. However, in this specific application, we are limited in the control actions. So you don't want to over-deliver. It's not a chemical plant where you can open and close the valves arbitrarily, right? So the result is that we may have suboptimal control. I agree with you with the LSTM, you don't know what's going on. Yeah.
Thank you.
All right, thank you again.